Okay. So we're going to focus on actually the first part of this presentation. We're going to talk about a fix for the valence bond theory. And then we're going to talk about the modern interpretation of bonding. But we'll do the fix a problem. You know, I've talked about this before. When a theory fails, you have, well, I've added an option. You have 4 options. And one of those is what we're going to do to the valence bond theory when it cannot correctly predict the shape of the molecule for methane. Remember, for the valence bond theory, the ideas behind the bonding is that orbitals overlap. So we have predicted with our Lewis dot structure that you should have a tetrahedral. I think I will close the door. The valence bond theory, I mean the VSEPR says that this should be tetrahedral. Okay. So which bonds of hydrogen would overlap? Well, hydrogen only has 1, so it's 1s1. But that orbital would have to overlap with carbon orbitals. Well, let's look at the electronic structure for carbon. Carbon is 6. Yeah, 6. So it would be a 1s2, 2s2, 2p2. Okay. We know the orientation of the s orbitals, they're spherical, right? So you can bond any direction on those. But the p orbitals are directional, right? They're on the x, the y, and the z axes. So we could get 2 of these hydrogens anywhere, and the other 2 would have to be on the one of these, overlap one of these orbitals. That's not going to give you a tetrahedral structure, right? But we know from physical evidence, from experiments, that the structure of methane is tetrahedral, right? So there's the problem, right? The valence bond theory in just simply overlapping atomic orbitals is not going to work. So, oh, and we measure the bond angles also, and they turn out to be 109.5 degrees, which is tetrahedral. Now, what do we do about that? Well, let's see. Okay, I've already talked about that. And we can't overlap these orbitals and get what we want. So I think it was Linus Pauling that proposed the correction, the modification to the theory that would solve the problem. And it's called hybridization. We're still making atomic orbitals, and the orbitals belong to the individual atoms. But in order to get them to assume the proper orientation so that we get the structure that we're looking for, we hybridize these valence orbitals. Okay. Okay. Yeah, I was right. Linus Pauling. In 1931, he proposed this modification to the theory. Now, I will say this, that the carbon atoms by themselves, pure carbon, will still have the S2 and the P2 electronic structure. But when the bonds start to form, that's when the hybridization takes place. Okay, it's only under the reaction circumstances that the hybridization is required, and it happens. So what we mean by hybridization is we take the orbitals, the valence orbitals that are going to be involved in the reaction, in the formation of the bonds, and we take these 4 orbitals, and we produce a hybrid orbital that we call an sp3. So we have 1s orbital and 3p orbitals. We know that that's atomic, and we form this sp3 orbital, and you have the same number of sp3s as the pre-bond atomic orbitals that go into it. So we have 1 of these and 3 of those. That means we have 4 of these. So we form 4 sp3 hybrids, and they are oriented to the apexes of the tetrahedron. Then when the bond forms, you get this tetrahedral structure. Okay. Now, I want to add one thing. The electronic structures we've discussed in the past are based upon the quantum mechanical models. In other words, Schrodinger's equations. No, that doesn't sound right. I probably have to edit the video and put the correct name in there, because it escapes me for the moment. But the quantum mechanical theory and the equations that go into it are also used to produce these hybrids. So it's not just like Pauling just pulled this out of thin air. I mean, he had to back it up with a quantum mechanical model to produce this structure. Okay, so when we form the sp3 hybrids, and we need those 4 sp3s to give us these bonds, then that allows us to produce the tetrahedral structure. And when we look at it in terms of energy, which is where we focus our attention, as far as Heisenberg's concerned, we focus on energies rather than absolute position. We have a relative probabilistic version of the shapes and the orientations of the orbitals, but we're more concerned about the energies. When we look at the energy of the p orbitals in the 2 level, they're higher than the s orbitals, and that's largely due to that penetration effect. But when we hybridize them, then you get an energy level that's somewhere in between. And since 3 p's were part of the mix, you're 75% from the s's to the p's. So they sort of overwhelm the s's, and the energy level of the sp3 is closer to the former p orbitals than it is to the s. And this is generally what the equations generate as a bond electron density orientation. All right. So there we go again. Now we don't have to hybridize the hydrogens. We only have to hybridize the carbons. The hydrogens only have 1 bond orbital available anyway, so they just overlap the best they can. Okay, how about the ammonia molecule? We're going to extend our discussion. Let me try these. Extend our discussion to the ammonia molecule, because if we work from the VSEPR, we know that ammonia should be tetrahedral also, electronically speaking, right? So if we draw the ammonia molecule, we have that hydrogen in the back, have 1 out here, have 1 out here. So they form that triangular base, and then you have that lone pair up there. Well, that electronically it's tetrahedral. Of course, molecular, it's a triangular pyramid. But the hybridization that's required, since nitrogen has actually 7 rather than 6 electrons, it would be 1s2, 2s2, 2p3. Let's see. Oh, I thought we were going to have more. Okay. So in order to use the hybridization, you still have to go through the steps. You've got to write the Lewis structure, which we've done, and determine the arrangement of electron pairs using the VSEPR. So now we're still tetrahedral electronic structure. And that's where we focus our attention for hybridization, is on the electronic hybridization, the electronic structure. Then we see, okay, what kind of hybridization do we need? There's our Lewis dot structure. Well, we have 4 pairs that are pointed to the 4 points of a tetrahedron. We need sp3 hybridization to give us those 4 orbitals. Okay, so when we do that, we get the sp3 hybrid orbitals like this, like that, and then this one contains a lone pair. So one of the sp3 hybrid orbitals contains the lone pair. And that's what it looks like. And of course, this hybridized orbital is still going to balloon some. So it puts pressure on these and decreases the bond angle from 109.5 down to, I don't know, 108, something like that. Okay. So let's see, what are we going to do with this one? Ethylene, C2H4. I was going to use these with that. So if we draw that one, we have 12 plus 4 is 18, right? 18 electrons. So we put the carbons together and the hydrogens out here like this. 2, 4, 6, 8, 10. And we have 8 electrons. Did I count those right? 16, excuse me. I added it up wrong, didn't I? 12 plus 4 is 16. 6 electrons. We have 2. No. I'm wrong again. Valence electrons. 2 times 4 is 8. Plus 4 is 12. There we go. 2, 4, 6, 8, 10. That's 10. So we have 2 electrons, and there they are. So we take these, we've learned, to make the octet, put that in a double bond. So that's ethylene. Now, what is the structure? Since we don't have any lone pairs, we can go straight to molecular geometry. We have 3 pairs here, right? Which is trigonal planar. Okay. There again, the carbon has 1s and 3 p's available, and they're not equivalent. We need 3 equivalent orbitals in there to do the job for us. All right. So how do we do that? Well, let's see. Trigonal planar, and bond angle is 120 degrees. Now, how do we get there? We can't get there with sp3 hybridization because that gives us 109.5 degrees. We need 120 degrees. So the solution to it is we don't hybridize all of the carbon orbitals. We only hybridize 1s and 2p's. That gives us 3. 1, 2, 3. So this is an sp2 hybridized carbon with one unused p orbital, 2p orbital. So we could represent that as like that. And this one would be the same way. Only we've got 1, 2, 3, 4, 5, 6, 7, should be 8, 6, no, 12, 12. I'm getting ahead of myself. sp3 hybridization is characteristic of trigonal planar, right? If we put that over here, let's do that. Let's say, let's see, number of bond groups, like we did with the DSEPR. So we started with methane, we had 4 there, and the hybridization required was sp3. There. So we had 1, 2, 3, 4, cover those groups. Now we only need 3, so that's sp2. Okay, here we go. So what happened to that extra orbital here? Well, we're going to talk about that a little bit more when we get to pi bonding. But these guys here overlap, and that produces the second bond, the double bond. Okay, we'll stop for a moment for terminology. When you have 2 atoms bonded together, there's always at least 1 bond on axis between the atoms. That's a sigma bond. The Greek letter, that's the small sigma. Sigma bond is always on axis. Then if you have a double bond, you can have 1 double bond, you can have 2 double bonds. We know that nitrogen has 2 of them. Those are called pi bonds. And they're always off axis. So the stronger bond is the sigma because it concentrates electron density in the bond on axis between the atoms. And if there's a double bond, it has to occur off axis, which means the overlap of orbitals is not complete. It's not as complete as the sigma. And this is the weaker bond. The pi bond is weaker than the sigma bond. Okay. So back to our energy diagram. When we do an sp2 hybridization, we're introducing less p character, more s character by comparison. So the energy level of an sp2 hybridized bond is lower. It's closer to the s orbital character. And then we have that 1 p orbital. It's the same as where it was before. Right? You have 3 sp2s and 1 p orbital that's left out. All right. This is a representation of what the orbitals would look like. They're probabilistic arrangement around the, in this case, the carbon atom. So the sp2s are pointing at the apexes of an equilateral triangle. There we go. All right, and this is what they look like, according to the theory and the calculations. Okay. So this introduces the idea of what do you do with that p orbital? And we see the yellowish orbitals are the ones that are hybridized, and they overlap with the hydrogens and with the neighboring carbons. And then those excess unused p orbitals do the overlap for the double bond. Okay, how about carbon dioxide? Let's look at that one. All right, we know that if we're going to have carbon dioxide, we have to start with the Lewis structure. So I'll get it right this time. 6 times 2. Yep, that's 12, 16 electrons. So we have the carbon in the middle, oxygen's on the outside. That's used up 4, so we have 12 left over. 2, 4, 6, 8, 10, 12. Okay, we're all done. Now we know from our formal charge calculations that the best way to make an octet around this carbon is to take 2 from this side and 2 from this side. Okay. All right. So with the carbon having 2 bond groups, we only need 2 hybrid orbitals from that carbon. So that would be an sp hybridized carbon. Okay. And it will produce, this would be, we would have 4 sp3s in this situation. We would have 3 sp2s here, and we would only have 2 sps here. This would have, let's see, unused, let's see, I shouldn't say unused, I should say non-hybridized, non-hybridized. P orbitals. This will work for a little while, and you'll see why in a few minutes. So we have 0 unused here. We have 1 unused there, and we have 2 unused p orbitals here. Okay. So this is going to be, and the bond angles here, I should stick this in here. Bond angle is 109.5, 120, 180. So the bond angle here is 180. But we can also hybridize the oxygens, and we have to do that. We hybridize the oxygens because they have 1, 2, 3 groups. So they're going to be sp2. This is sp hybridized. These are sp2 hybridized. Okay. Which means this one has 2 p orbitals, and each one of these has 1 p orbital each that are not hybridized. Okay. These are non-hybrid. And these are hybrids. Okay. So we get these 2 sp orbitals, one going this side, one going that side, to overlap one of the sp2s from this oxygen and the other sp2 from this oxygen. Well, that leaves an extra that leaves an extra sp2, 2x sp2s on this side for the lone pairs, and the other 2 sp2s on this side for lone pair, for those lone pairs. But we still have this unused, at present, unused p orbital here and 2 of them here. So one of these unused p's overlaps with that one and gives you this double bond. And the other one overlaps with that one and gives you that double bond. And that's what the pictures are going to show in just a second. Okay, there's our linear bond angle. Okay. Oh, we're going to do energies first, right? Yeah. All right. So since we've got more S character, we're closer to the S now than we were with the sp2s or the sp3s in energy for the hybridized orbitals. And the unused, of course, are still at the same energy level as before. And that's what they look like. So there's the sp hybridized carbon with its green orbitals, hybrid orbitals, and then the yellow hybrid orbitals from oxygen. And we're overlapping those the sp2 hybridized orbitals give two lobes with lone pairs. And the pi bond is formed by the unused p orbital from either side. And they have to be, well, for our visualization, they have to be rotated 90 degrees from each other in order to get the proper overlaps. Okay. How about N2 nitrogen? Let's see. Let's get rid of that one. And let's see what we can make of this one. Okay. That's 10 electrons. So we have like that, equals 8, 2, 4, 6, 8, right? And we need to make a, no, that's not right. Nitrogen is 5. Well, that's right, 10. And we're minus 2 here. That should be right. 2, 4, 6, 8. Okay. So we take that one, make a triple bond. So now we have a triple bond between the nitrogens and lone pair on each one. Okay. So electronically, of course, we have VSEPR says we have linear electronic on either side. So the whole molecule is linear. Well, it has to be because there's only 2 of them. All right, what about the hybridization? How do we get linear out of this? We have sp hybridized. Sp. That gives you linear. And we have 2 p's unused for each one. One of the p's from each side makes a double bond, and the other p's from the other side makes another double bond. That's how we get our triple bond between nitrogens. All right, sp hybridized, there we go. And 2 unused p orbitals temporarily. So we have 1 sigma bond and 2 pi bonds. And these both these pi bonds are off axis. There can only be a partial overlap as compared to the on axis sigma. All right. So this is what the artists think it looks like. Now, here comes some fly in the ointment, so to speak. PCl5. All right. Phosphorus is 5, and this is 5 times 7, so it's 30. Let's see, 40, right? 40 electrons. We've done this one before. So we put phosphorus in the middle, and the chlorines all around. Right? 2, 4, 6, 8, 10. That means we have 30, or 6. 6 times 5 uses up all of the electrons. No lone pairs. Well, I shouldn't say no lone pairs. I say no lone pairs on the phosphorus. Chlorine's got a bunch of them. So we've used up all our electrons. And what's our structure here? If we have 5 bonding groups, then let's see, this one's tetrahedral, this one's trigonal planar, this one's linear, this one is trigonal bipyramid. Okay, so it's going to look something like phosphorus in the middle, and we're going to have chlorines here, chlorine there, chlorine there, chlorine there, chlorine there. So the bond angles there will either be 120 or 90 or 180. Those are the possibilities. All right. So phosphorus, what's the phosphorus electronic structure? Let's see, it's in the third group. So we're going to have 15. Chlorine's only going to overlap once here. So chlorine does not have to hybridize at all. Phosphorus does. And here's why. It has 1s2, 2s2, 2p6, 3s2, and 2 and 3p3. Right? Let's see, 8, 11, 12, 13, 14, 15. That's good. Okay, we're going to be using the valence electrons. So there are 5 of them. But if we just hybridize the S's and the P's, we only get 4 bonds available, 4 orbitals available. That's not enough. We need another one. So notice that phosphorus has access. What else do we have in the third level? We have D's. So we're going to take one of those D's and hybridize DSP3. Now don't ask me why we put the D first. Because energy-wise, D comes over here. But DSP3 hybridization times how many? Well, 3, 4, 5 times 5. Okay. Now, in this case, we don't have any unused P's. I guess you could say we have unused D's, right? Because there are 5 D's. We have 4 unused D's, but we only call on them if we need them. Okay. So the shape that molecule is trigonal bipyramid, bond angles 90, 120, and 180. And this hybridization will give us the 5 hybrid bonds that we need to make this regular structure. Let's see. And there's what it looks like. Artist rendition. Okay. We didn't do the energy diagram on this one. I guess that's a little too much. Xenon tetrafluoride. Right. We have 8 here, 4 times 7 is 28. So we have 36 electrons. Chlorine, chlorine, chlorine. Excuse me, 2, 4, 6, 8 equals 28. 2, 4, 6. 6 times 4 is 24. So we have 4 electrons left over after we place them all around the fluorines. That means we have 2 there, 2 there. Okay. So we have 1, 2, 3, 4, 5, 6, right? 6 groups. And that says octahedral, according to the VSEPR. So what are the bonds we have there available? Well, let's see, we have this square in the middle, xenon here, and then we have fluorines. Actually, no. Lone pairs go on the apex. There we go. So that would be the structure there. And since we were called upon to use 6 hybrid orbitals, we're going to have to take another D. That gives us 6 hybrid orbitals, 2 Ds, 1 S, and 3 Ps. And the bond angles are going to be 90. Well, molecular bond angles, yeah, just 90. All right. If we have these occupied, then it would be 180 is possible. But if you have both of them occupied, if only one of them is occupied, you're still 90 degrees only. All right, so 90-degree bond angles. Here we go. All right, that's D2sp3 hybrids. Let's see. And we confirmed it, of course. I think we've done this before. Experimental confirmation, right? And one of the evidences is that each of these bonds is going to be polar, right? If those fluorines were anywhere else, then this would have a dipole moment. But since it's non-polar molecule, and that's been verified, that's the only arrangement that can give us non-polar. Okay. And we have 2 D2sp3 orbitals right here that are reserved for those lone pairs. All right. So this is where we are up to now. Out of order according to that. This one, this one, this one, then that one, that one. But that is like we did with the electronic structures in the VSEPRs when I laid those out. Similar here. Notice that when you have 2 groups, sp hybridized. If you have 3 groups, sp2, 4 groups, sp3, 5 is dsp3, 6 is d2sp3. So you just add up the numbers, right? You know the limits on p's and s's. So when you get past that point, you have to add a d or 2 d's. So it's fairly logical, actually. I mean, once you've got the VSEPR in mind, it's just a small step to go to this next level. All right. Let's see what we got going here. Hydrogen cyanide. Draw the Lewis structure. Okay, we've done this one before, so we don't have to dilly-dally around. There we go. Let's see, let me count up my electrons to be sure. 2, 4, 6, 8, 10. 1, 6, 4 is 10. Okay. So there's your Lewis dot structure for hydrogen cyanide. This one is going to be a sigma. That one's a sigma, and these 2 are pi's. Okay. Let's see. Both of these have to be hybridized SPs because this, when you look at carbon, it has 1 and 2. Right? It only has 2, so it has to be SP hybridized. This has 2, that one, and a group on either side. This one has to be SP hybridized. Now, one of these SPs is used for a sigma bond on that side, and one is used for a sigma bond on that side. And then the unused p orbitals from either side, since we've got 2 extra p orbitals here and 2 there, they overlap to give us these 2 pi bonds. There we go. Sigma, sigma, pi, pi. Okay. So now we got a nice list. We want to see if we can make sense of it. All right, we did ammonia already. So we should be able to knock that one out. Bond angles and hybridization. The bond angles nominally here are 109.5. And hybridization would be sp3. We did carbon dioxide before. Let's go ahead and knock that one out. Carbon dioxide should be sp hybridized with 180-degree bond angle. And the others we haven't done yet. So we'll do sulfur dioxide. Actually, that one should be like water. If we draw the structure, sulfur is 6. Yeah, 3 times 18. So we have an SOO like that, 2, 4, 6, 8, 10, 12, 14, 16. Missing 2. I count that right. 2, 4, 6, 8. S is, yeah, that's 6. 3 times 6 is 18. What did I do wrong? Did I do anything wrong? No, I didn't do it. That's right. It's not like water. I'm thinking of hydrogens. Okay, so this has 3 groups around it. It should be trigonal, planar, electronic. So that would be 3 would be sp2 hybridized. Okay. And the bond angle should be 120 degrees. Okay, let's see. Did I animate this one? Yeah, there we go. Yeah, and I'm going to do, oh, it's probably taken in that direction, so we better do this before I steal my own thunder. Okay, so that's 8, and 2 times 7 is 14, is 22. 22 electrons. So that's 2, 4, 6, 8, 10, 12, 14, 16. Which would be what? 6, 2, 4, 6. So around that krypton, we have 5 groups, which should be DSP2. And that would be, electronically speaking, it doesn't ask us to do that, does it? That would be trigonal bipyramid. So in a trigonal bipyramid, where do the lone pairs go? They go around the triangle, right? So that means the bond angle is 180 degrees. Yep, and it's non. Okay, I threw that one in free. Non-polar. Doesn't ask for it, but I give it to you anyway. Okay, CO2 is probably next. We did that one already. And then iodine pentachloride. So 6 times 7 is 42 electrons. And if we have I there, and then 1, 2, 3, 4, 5. Two, 4, 6, 8, 10 would be 32. And then 6 times 5 is 30. So we have 2 electrons left over. They have to go here. This is going to be electronically octahedral. So it's D2sp3, octahedral electronic. So where does that lone pair go? It goes at the apex, one of the apexes. So sometimes I have to draw these things out to see them. Iodine in the middle, and we have a lone pair up here. But we have chlorine down here. Actually, I should have done it the other way around. It's a little easier to visualize with the lone pair down here and the chlorine up here. So there are your 5 chlorines. Bond angles, all 90 degrees, because you don't have a chlorine down here. Oh, D2S, I did that already. D2sp3. Okay. All right. So this is just a reminder. When you use this hybridization scheme, For the localized electron model, you have to work your way through what we've done before and then say what type of hybridization is required to get there. All right. So now we're going to throw stones at the localized electron model and valence bond theory. What's wrong with this model? Well, by now we probably, and chemists had figured out that if we have to do this type of fix to it, then it's probably not right. Because we're assuming electrons are localized on each of the atoms and they're only shared to form the bond, overlapping orbitals. We have to add resonances sometimes and hybridizations in others. They also do not effectively account for free radicals. Free radicals would be, we'd have just one electron sitting up there. I think we did one of those structures before with nitrogen and oxygen involved. So it doesn't effectively account for free radicals. What do you do with those? We can suppose certain bond energies, but we cannot calculate them exactly. Bond energies are off limits to this model. All right. If we needed it, this is where I would pause. But we're good to go, and we're going to keep on rolling. So our solution to the problem is called the molecular orbital model. Okay. Or as I like to call it, chemical communism. In other words, when you form the molecule, the electrons belong to the collective. The whole molecule owns those electrons, and it puts them in a new set of orbitals, molecular orbitals. So now we're not claiming each atom has possession of the electrons and they only share them as far as the bonds go. Those electrons are put into a new set of orbitals, molecular orbitals. Now these came, historically speaking, this came after the valence bond theory and the localized electron model and all the fixes we had to put in there. And it is based upon quantum mechanical calculations. Let's see. All right. That's right. The orbitals extend over the entire molecule. We're still calling them orbitals, and that's grandfathered in from as far back as Niels Bohr's model, his planetary model. Right? Just understand that they're really not orbitals in the classical sense. All right, let's compare the two. Localized electron model versus the molecular orbital model. Let's see. First, the biggest difference is the localized electron model relies on atomic orbitals, and the molecular orbital model creates a new set of orbitals, and the atomic orbitals disappear when the molecule is formed. They're both quantum mechanical. Only the localized electron model continues to treat them as extended atomic orbitals into the molecular arrangement, whereas the quantum mechanical solutions to the molecular orbital model are entirely new. It doesn't retain any of the mathematical characteristics of atomic orbitals. We assume electrons are localized on atoms, whereas the molecular orbital says the electrons are delocalized. Whenever you hear that word, if you can get delocalization in a molecular structure, that adds stability. When you can spread that lowers the energy and causes greater stability for the molecule. Delocalization is a good thing for molecular stability. We still have, in the molecular orbitals, each orbital can only hold 2 electrons. One spin up, spin down, just like before. The chi-squared wave function is solved for atomic on the localized electron model, and solved for molecular orbital for that one. And the energies are still quantized. In other words, even though you have a new set of molecular orbitals, you can only have certain energies allowed, nothing in between. So that's brought over into the molecular orbital model. All right. So when we create these molecular orbitals, we start from the atomic orbitals, and we take them to produce the molecular orbitals. And one of the chiseled in stone rules, you have exactly the same number of molecular orbitals in a molecule as you had atomic orbitals going in. So, and we're not just concerned with valence orbitals, although we'll draw them in that way, and we'll let the molecular orbitals that are formed from the non-valence core atomic orbitals, those molecular orbitals are usually below screen, and we're focused on the molecular orbitals formed from the valence shells only. That's just for convenience. Just remember that when the molecular orbitals form, everybody gets in the mix. So if we have 2 atomic orbitals, that produces 1 bonding and 1 anti-bonding. That's how we do it. We don't produce, out of 2 atomic orbitals, we don't produce 2 bonding orbitals. In order to make the system work, if you have 2 atomic orbitals going into the mix, then you get 1 lower energy bonding orbital and 1 higher energy anti-bonding orbital. And I'll show you the terminology in just a minute. Oh, I think I do have I hope I have a video coming with this. And that bonding versus anti-bonding is not, we didn't pull that out of thin air. It's based upon a concept called resonance and interference of wave functions, right? Have we talked about that before? Yeah, wave functions. When you have 2 waves encounter one another, and if they're both synchronized, you get, let's see, plus here, and you get constructive interference. If, however, they're offset perfectly by 90 degrees, like that, then what you get is that. Well, in the atomic realm or the molecular realm, when we're building these orbitals, the quantum mechanical equations give us values that are akin to constructive versus destructive interference. The constructive interference gives us bonding orbitals. The destructive interference gives us anti-bonding orbitals. So it's not just a pipe dream. It's based in, well, it's based in mathematics. It's not that we've observed them. And if the molecular orbital is centered along between the atoms, that is a sigma molecular orbital, right? And if it's off axis, it's a pi molecular orbital. So we retain that terminology when we're constructing these molecular orbitals. Yeah, this is it.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay. So this concept of constructive and destructive interference leads to, for our purposes, bonding versus anti-bonding orbitals. So we call that, when these two overlapping waves add together, we call that superposition. And the summation of their wave heights give us that, whatever it happens to be, whether it's destructive or constructive interference. And the interaction itself is called interference. Right? So we've defined those already, what constructive and destructive are. We can form very complex patterns, though, if the waves are not of the same frequency. Then they would tend to produce very complex interference patterns. And actually, we use that to our advantage in communication in the old days when radio was just AM. Okay. What would happen is you would have the microphone would be, say for a talk show, would have waves coming in and convert it into electrical signal, and these would be like that. And then we would superimpose this one on a carrier wave. So we get some complex. And the interference pattern would be broadcast to another receiver, right? The receiver would take it, and then it would destructively interfere with this same pattern and reproduce that pattern. This is the information or data part of the wave, and this is the carrier. So these calculations are extremely complex, especially if you start introducing them into molecular structures. So it's not something that is easily done by hand. All right, here's what the 1s orbital of a hydrogen with an s orbital of another hydrogen would produce. On the bottom, you see the constructive arrangement. That's the bonding orbital. And notice that you have predicted electron density between the hydrogen atoms is where it's concentrated. The anti-bonding, however, is concentrated away from the hydrogens and not between them. And that position in the middle is still called a node. Did we use that term before? A node, yeah. A node means there's no probability. Yeah, we did use it. No probability of finding electron density there. That's characteristic of anti-bonding molecular orbitals. And the way we would write it is, we would have this bonding orbital at a lower energy, and at a higher energy, we'd have an anti-bonding orbital. We use a star to mean anti-bonding. I mentioned this already. Bonding orbitals usually are always lower energy than anti-bonding orbitals. So this is one method that we use to try to construct the molecular orbitals from atomic orbitals. So this is our energy from low to high, and we have our atoms here with hydrogen would be a 1s1, and this hydrogen over here would be 1s1 as separate atoms. Okay, so we would have this 1s on this side, we'd have this 1s on this side at some level of energy, and they're at the same level. And when they go into the mix, and this one has the combination. This is the molecular, this is atomic, this is the molecular. And then we draw dotted tie lines. So this is going to produce a 1s, let's see. It's a sigma bond formed from the 1s orbitals. And this one produces a sigma star from the 1s orbitals. There you go. And then we came into this with one electron here and one electron there, correct? So we have to have the same number of electrons, and we use the Aufbau principle. We fill from lowest energy to highest energy. So this molecular orbital can hold 2 electrons. You have to flip the spin on one of them. But they're both accounted for in this molecule, and both of them are in bonding orbital. So that's good for forming the molecule H2, diatomic hydrogen molecule. That is the simplest demonstration of molecular orbitals right there. They can get more complex real quick. Okay, I'm assuming that since this bonding orbital and anti-bonding orbitals were made from 1s's, and these are spherical, that this sigma is probably has at least a simulated spherical shape. It's probably oblong because it's bonding. Right, so we generally defer to the atomic orbital orientations, but it's not absolutely necessary. Let's see. And we can write, you can also write an electronic structure for the molecule now. So we would write lowest energy to highest energy. So this one we would start in a shorthand version. We would say this one has 2 electrons in it, and this one has none. So actually, we wouldn't even have to put that one in there, right, because it has no electrons. This would be the molecular orbital structure for dihydrogen. All right. So how about, let's see, are we going to do fluorine? All right. That's a big jump to go from this to that. I might be able to put that together. Let me see. Should I poke the dragon? Fluorine, fluorine. Okay. So fluorine is going to have 1, 2, 3, 4, 5, 6, 7, 8, 7. Excuse me, 7. Has 7 valence electrons, but 9 has 9 total electrons. So we said that we would go from 1s, right? 1s, and then 2s. That might be a little close. Let's put 2s up here. And then 2p, right? Yeah, that should work. 2p, 2p, 2p. Let's be on top. This one has 3. S and 1s. There we go. So we're starting off with 2, 4, 5, 6, 7, 8, 9. Right there, like that. Now, how do we form the molecular orbitals? Well, we're going to have one here, one here, there, one there. Those are the easy ones. This one's going to be a sigma star from the 1s and a sigma star sigma from the 1s. This one's going to be another sigma from the 2s and a sigma star from the 2s. Then we're going to have 1, 2, 3, 4, 5, 6. Got to have 6 orbitals here. One of them is going to be a sigma. So it's going to be a sigma from the 2p. And then up here at the highest level is a sigma star from the 2p. Then we're going to have 2 here and 2 here. This one's going to be a pi and a pi. So this is a pi from the 2p. And this one will be a pi star from the 2p. There we go. So we have 1, 2, 3, 4, 5, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 orbitals made out of those 10 of the atomic orbitals, molecular orbitals. So this one is going to be F2 with 18 total. Okay, so we got 18 electrons. So we put 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we don't need that one. Okay. So that's where this arrangement comes from here. So if we take it and take this and just turn it 90 degrees, it'll look like 1s2 sigma star 1s2, sigma from the 2s. This one's a star. It has 2 electrons in it. And then we'll have 2p from a sigma. And then we'll have a pi, 2p. We can have 4 of those. We have 2 of these here. All right, so we can have 4 there. We can have 2, 4, 6, 8, 10, 14. And then, yeah. And then this one is a star with 4 in it. So that should be 2, 4, 6, 8, 10, 12, 16, 18. That's it. So that would be our abbreviated version of writing the molecular orbitals for difluorine. Now, if it only asks for the valence, we would just do the same as before, right? Principal quantum number, 2s, 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 and we would only include that part of the molecule. Okay. Now, one of the advantages of this method is the ability to calculate what's called the bond order. Now, the bond order is loosely equivalent to single, double, triple bonds. The difference is that when in the past, when we said single, double, and triple using the valence bond theory, we only had whole numbers available. It was either single, double, or triple. With bond order, we can have fractional bonds. Right? And the way you do it is you take the number of bonding electrons. In that case, we would have how many? Right, this is bonding, so that's 2, 4, 6, 8, 10. 10, and subtract the anti-bonding electrons. So here we have 2, 4, 6, 8. And then you divide by 2 for the 2 electrons in each orbital. So that it gives you a bond order of 1, which implies a single bond. And that's what we've shown from previous theories, is that this is our valence bond version, our Lewis dot structure for difluorine. It's got that single bond, right? So in this case, the bond order agrees with our previous assumptions, but they don't have to be whole numbers. Hopefully, we'll run across. If we did the same thing for hydrogen, we just say 2 minus 0 divided by 2 is 1. So dihydrogen has a single bond. What would happen, okay, I should have left hydrogen up there, but I couldn't help myself. It will take just a second to redraw it. Actually, we don't have to redraw that structure because we know that dihydrogen has a sigma made from a 1s, and both electrons are there. Okay. The next highest orbital is the sigma star from a 1s. If we turn this into an anion, if we add an electron, where does it go? It has to go right here, doesn't it? Okay. So if we calculate the bond order of this one, we have 2 bonding minus 1 anti-bonding divided by 2 is 1/2. So the bond order is 1/2 versus 1. We have weakened the bond. Instead of 1, it's a 1/2. Now, this ion we can create this ion, but it's not as stable. It has a weaker bond. Oh.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have two isolated hydrogen atoms. And we know that each isolated hydrogen atom should have one electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when two atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those two 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the two hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these two nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have one more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma-pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons. We expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
I like to let the credits show, so they don't haul me off to jail for violating copyrights. Okay. So there was a mention of paramagnetism. We're going to cover that in just a few minutes. What we saw as examples in this video were simply homonuclear diatomic molecules. In other words, both of the atoms that went into the molecule were the same element. Those are the easiest to understand and draw. Now, these terms, paramagnetism versus diamagnetism. A paramagnetic substance, in this case, a pure substance, can be attracted to a magnetic field. A diamagnetic is repelled by that field. So if we tried the same experiment, I think I've got a slide coming up. If you pour liquid oxygen into, you've seen these big, huge horseshoe magnets where they come together like that. And they've got an extremely strong magnetic field. You don't want to get near one if you've got a pacemaker. If you pour liquid oxygen into it, it'll stick. It'll stay right there in the field until it evaporates. If you pour liquid nitrogen in there, it'll go straight on through, won't stop. Our previous understanding, based upon the localized electron model and the valence bond theory, predicted otherwise. It predicted that oxygen should be diamagnetic. So that's another place that it failed. You can measure the strength of this attraction or repulsion. This is a stylized artist version, but it's not too far from the truth. You have a very sensitive analytical balance, and you lower your sample into this strong magnetic field, and you measure with the balance whether it's pulled or pushed. And there, oh, there's our example, oxygen. Pour liquid oxygen into that magnet, it sits right there in the field, magnetic field, until it evaporates. Oh, Professor Dave wants to talk.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of 2 atomic orbitals will always result in 2 molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with 2 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put 1 electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
No, we don't want to hear from you again. So this is this was that diagram that he showed you, and you'll notice that it's in the useful information in your review document, which means it'll be available on the exam. The place where you get that flip, that switch, is between oxygen and nitrogen in this group. So if you go to the left, then you're gonna get the pi bonding orbitals first, then the sigmas. But from oxygen and fluorine across, you're going to get them in the order that we see them with hydrogen. Yeah.
This all gonna be on YouTube.
Yeah.
Yeah. This is good.
You get a copy of everything?
Yes.
Okay. All right. This is another way of looking at it. And this is also in your review document. But it actually, rather than just showing orbitals, it shows certain homonuclear diatomic molecules and their molecular orbital structures. And you'll see that the boron, the diboron, dicarbon, and dinitrogen are experiencing mixing. But like Professor Dave said, it does matter when we're talking about paramagnetism and diamagnetism. Bond order doesn't matter because you're just totaling up bonding versus anti-bonding electrons. But when you're discussing the paramagnetism versus diamagnetism, the bond order does matter because the order in which the electrons go in determines whether you have paired or unpaired electrons. If you have any unpaired electrons, the molecule will be paramagnetic. If they're all paired, it'll be diamagnetic and repelled by a magnetic field. So we get this list here with paramagnetic under diboron, then diamagnetic carbon, diamagnetic nitrogen. And then we get a paramagnetic oxygen, and you can see where the unpaired electrons are located. And then difluorine is also diamagnetic. And the bond order is calculated for you there. And then the bond energies are provided there. And you notice the same pattern is observed as you go from a single, double, triple bond. You increase the energy of the bond, but it's not linear. In other words, the double bond is not twice the single bond. Actually, you know that I never noticed that before. The carbon forms a double bond. Dicarbon forms a double bond, but it's a stronger bond. It's more than twice the boron. So can we deduce something from I can't give you a good explanation right now, except that the pairing of electrons seems to stabilize things. I'm not going to ask you that question because I can't figure it out. All right, so there, that's the way I look at it. You get the switching when you get from nitrogen to oxygen in that period. You get the mixing to the left of oxygen and no mixing to the right. Come on, there we go. Sometimes they, instead of SP mixing, they call it sigma pi mixing, which is actually the proper way to describe it, because we're talking about molecular orbitals, and they're either sigmas or pi's. SP is still referencing atomic orbitals, but the name stuck, so you'll hear it both ways. So now we have the opportunity to look at heteronuclear diatomic molecules. In this one, we're looking at carbon monoxide, 1 carbon and 1 oxygen. And this should give us a bond order of 3. Right? Carbon monoxide has a triple bond. So the carbon comes in 2 positions to the left of oxygen, which means that with a lower nuclear charge, the orbitals are going to be higher in energy. They're not drawn as close to the nucleus as they are with oxygen. So that's why the atomic orbitals for oxygen are lower than they are for carbon. And then when you combine them, if the orbital energies are close enough, you'll get a traditional non-mixing version. And it looks like we do. We get the sigma from the S's. Yes. No, there's a reverse there. Notice, I just noticed that. We would expect the sigma star to be way up high, but it's not. It's right in here. So that order is something that I can't calculate. You'd have to be given that in order to make sense of it. But if you were given that arrangement, then you could probably fill in the electrons from lowest to highest. And if we calculate the bond order, it looks like there are 2, 4, 6, 8. Bonding minus 2 anti-bonding would be 6 divided by 2 is 3. So the bond order is 3 for this molecule. HF is a little bit different. And it looks like this. Of course, with hydrogen, you've only got 1 proton and 1 s orbital, so it's going to be fairly high energy. And with fluorine, you have 9 protons, so you're going to have fairly low energy. And in this case, you don't get an overlap of what we call sister orbitals in both of them. In fact, the energy of the 1s for hydrogen is so high that it actually forms molecular orbitals with the 2p from fluorine. But once you do that and you populate the orbitals, we find out that it comes out with a bond order of 1, as expected. Okay. But we also see and are represented by this diagram. Let's go back to the diagram here. You notice that the sigma orbital, the sigma molecular orbital, is at an energy that's closer to the original fluorine, which is another way of saying those electrons are going to spend their time closer to fluorine than they are to hydrogen, because the hydrogen starts off with a higher energy. And that's what we actually measure. We measure a polar bond with fluorine as the slightly negative side. Okay. Let's see. Okay. I think the last topic we're going to talk about is delocalization. We mentioned it earlier. If you can delocalize the electron density, then you can stabilize the molecule. So what we're going to get into now is sort of a combination of the localized electron model and the molecular orbital model. I don't think this is actually how it happens in real life, but this is how we visualize it. So it helps us make sense of it. And we're going to use benzene as our example. If we drew benzene, which is C6H6, right? And its empirical formula would be CH, right? Just test it. It forms a ring structure. And you can draw it several ways, but if you draw it this way, which is actually improper, you're saying that there's a double bond here and there's a single bond there. Well, if we do it that way, which is required by the valence bond theory, we would have to move this one over here, that one there, and that one there, and resonate the two. And each one of these has a hydrogen attached to it. In organic chemistry, we simplify things so that they don't get too cluttered. And we don't even draw in the hydrogen atoms. And wherever two lines meet, that's a carbon. So we don't draw them in because it gets really messy. But this is the way we would draw it for the valence bond theory. And we would hybridize those carbons. We'd have 1, 2, 3 on each carbon. It would be an sp2 hybridized carbon if we used the original molecular orbital model. And what that allows us to do is we've got an extra unused p orbital on each one. So rather than these p orbitals simply overlapping, like these two overlap here, these two here, and these two here, you get a more extensive delocalization where all of them overlap and they form sort of a donut of electron density in what we normally would see as a double bond, but in this case, it's delocalized so much it's over the entire molecule. This is characteristic of, this is an aromatic system, and it's also characteristic of conjugated single double bonds. So you can have a chain of carbons stretching down like this, and we can attach stuff to them. But if every other one is a double bond, then you'll get that delocalization like you see here, and stabilizes the molecule. Those are called conjugated systems. Here's another example with a nitrate ion. We would have to resonate 3 structures with the original model that we talked about. And if we draw it like I showed you before with the half bonds, then what you actually have is a delocalization over the entire molecule. And this sort of points to this. It's not exactly like, but it points to the molecular orbital model, because we're further delocalizing electron density over the molecule, which the molecular orbital does by its very nature. Oh, by the way, I looked up while that video was going. Schrodinger is correct. His equations are what's used for the quantum mechanical models. Now, they've been modified extensively over the years by other researchers, but they started with Schrodinger. Okay, and the last thing here is experimental evidence. This particular method of analysis, the photoelectron spectroscopy, is used by determining the energies of electrons in individual atoms and molecules. And we do that by striking the molecules with high energy photons. And if you know anything about the photoelectric effect, have you ever studied that? Okay. The photoelectric effect says, and it's usually in reference to metals, we have a photon coming in, and if it's at the right energy, if it has a minimum threshold energy, it will eject an electron. If it's exactly the right amount of energy, that electron will be as far as the metal is concerned, at infinity, but only at the surface of the atom, just far enough to be removed from the atom, but it has no energy of its own. So it just kind of sits there. If we increase the energy greater than that value, then we impart some kinetic energy to that electron. Okay. And you can do that with other molecules too, and that's what we're doing here. When these high energy photons are directed at the sample, they produce kinetic energies based upon how far the electron has to move from its orbital to infinity. So for the outermost electrons, they'll have the most kinetic energy because it only takes a little bit to get them loose. But then the next layer down will absorb more of that energy to get them loose, and they'll have lower kinetic energy. So that's what we're showing in this diagram. The ones that are further down in the molecular orbital model take more energy to get loose. And so we've ordered them there. And they're quantized energy values that are measured by this procedure correspond with the calculated values from the model. So that's confirmation for that we're on the right track. Okay, I think that's it.